The Bird That Killed Arbitrary Code Guard for Ionescu. En marzo de 2017, Microsoft lanzó Windows 10 Creators Update, con grandes mejoras en su tecnología Arbitrary Code Guard y la habilitación oficial de la mitigación de Esta en navegador Edge. En la práctica de mitigación, desafortunadamente, salió rota. Microsoft ahora lo ha parcheado, y esta charla discutirá los detalles técnicos detrás del descubrimiento y el poder de este nuevo componente escondido, así como también los arreglos que fueron hechos para mitigar los ataques. Ionescu es jefe de arquitectura en CrowdStrike Inc. Es un arquitecto en seguridad y consultor experto en sistemas de software de bajo nivel, desarrollo del kernel, trainer en seguridad e ingeniería inversa. Durante sus estudios en ciencias de la computación, Alex trabajó en Apple en el kernel iOS, cargador de arranque y drivers en el equipo de plataforma central original detrás de iPhone, iPad y Apple TV.
Hello, everyone. Thank you. Thank you. So I'm here to talk to you about the bird that killed Arbitrary Code Guard. And if you're confused why we're talking about birds, you'll find out soon enough. So I think I already got a great introduction to Spanish, but I'll do the short English one. Currently Vice President of EDR at CrowdStrike. Most of my knowledge in Windows has come from reverse engineering Windows for the last 18 years, since 1999. I've worked on a project called ReactOS, which some of you may know about. And I was the lead kernel developer there for many, many years. And after that, I went to Apple, helped publish the Windows Internals books. The 7th edition has recently come out, so I do hope you get a chance to buy it. And in my free time, I like to give conference talks about Windows security issues, design flaws, and interesting hidden aspects of the kernel and how they can be abused. So today I'm here to talk to you about Arbitrary Code Guard. If you don't know what Arbitrary Code Guard is, it's a new mitigation that was added in Windows 10 by Microsoft, which is increasingly being used in new versions of Windows 10, and I'll talk a little bit about Arbitrary Code Guard and what it does. I'll follow up with some improvements that were done in Creators Update, and specifically how those improvements relate to a component called Warbird. That's the bird that killed Arbitrary Code Guard. So we'll talk about a bypass of the ACG mitigation using the Warbird technology. A bypass which still works as of today in the currently released version of Windows, regardless of your patch level, which will only be fixed in the false creator update, which is going to be coming out in about a few weeks. So we'll talk about kind of why this wasn't fixed and why it's taking so long. All right, so let's talk about Arbitrary Code Guard. So if you're thinking about exploitation, the end game of most exploits is going to be typically twofold. Either I want to get native arbitrary code execution, or I want to corrupt memory, right? So we talk about code execution vulnerabilities or exploits and data-only corruption. If your goal is arbitrary code execution, you then have a few ways of achieving that. One way is code reuse. There's already some code there, and you now use that code to do something malicious. Think ROP, JOP, COP, and those kind of control flow integrity violations. The other possibility is code generation or code modification, where you create new executable code and write into it, or you take existing executable code and modify it, right? So your virtual alloc, your virtual protect type of attacks. The third type is code loading. So this is when you can convince an application to load a custom DLL. So you're not really generating code, you're not reusing code, you're bringing in existing code off the disk, off a network share, off somewhere where it shouldn't be coming from. So if we're targeting the second attack here, usually what we're going to want to do is to basically figure out, is there some way that we can prevent you from generating code, or that we can guarantee that the generated code is safe or known generated code. Now, analyzing the generated code to try to figure out if the code is malicious or not is pretty hard to do. It's an open-ended computer science question. We're not going to solve it anytime soon, and you get very close to the halting problem. You could say things like, well, the generated code has to be signed, or it has to be produced by something that is signed. But then you have to trust that the signed thing is generating good code. And you have to make sure that the thing that's signed and is allowed to generate code is itself not compromised. But those are potential ways of kind of mitigating code generation. The other approach is to employ what we call W XOR X. And the idea behind W XOR X, which means write XOR execute, is that memory can only have one of two attributes. Memory can either be executable, but not writable, or memory can be writable, but not executable. You cannot violate this invariant. Write XOR execute. So you can technically generate executable code if we let you, but because it's not writable, you actually can't generate anything. You can have an empty page full of zeros, so add RAX, EAX. That's the only thing you can generate. So most operating systems are probably going to block that anyway. So with this kind of approach, you have a pretty solid kind of foundation to block code generation type exploitation, and this is what Arbitrary Code Guard is. It's Windows' implementation of W XOR X. This is implemented in the kernel through a function called mi arbitrary code blocked, and it basically verifies if your process has the mitigation enabled. It's something you have to opt in. Then, if the process is mitigated, we check if the thread has a special permission to bypass the mitigation. For legacy compatibility reasons, you could say that one thread can still do this within a process. If this is not that kind of special thread, we block the operation. This function is going to return a failure and it's going to trace. Otherwise, if you are allowing dynamic code, you can also enable auditing of dynamic code, basically being notified that something is trying to do this, which is helpful for Defender, ATP, and other EDR products. And this basically also generates a trace. Otherwise, if we're good, we also generate a different kind of trace. So what's up with all this tracing? Well, we're talking here about ETW, event tracing for Windows, which is the infrastructure that's been there since Windows 2000 to produce events in the event log and other tools that can collect them about what's going on with your system. And so you can enable ETW events to know whenever someone has violated ACG, and there's two ways of doing that. There's one kind of metric available for kind of IT troubleshooters, which is the kernel memory ETW channel. And in Creators Update, there's a Microsoft-specific security mitigation channel, which will tell you if the mitigation has hit as well. So there's basically two ways of knowing through tracing, even though you haven't blocked dynamic code, that someone is trying to use dynamic code, or that someone's been blocked from using dynamic code. So defenders out there, you can plug into this. Now, where are these checks made? Where do we actually check if you're allowed to generate arbitrary code guard? Well, we do them in NT-allocate virtual memory. So if you're trying to allocate virtual memory with page execute permissions, we're going to check for that. We do it in NT-protect virtual memory. So if you're trying to change the protection of memory, we can detect that. And we also do it if you're trying to reset permissions of a page, which is a kind of a clever way of changing a permission. By doing a reset, we also don't allow that. Finally, we don't let you map an image file, because that's executable code, that's arbitrary, and we don't let you map a data file as executable either. So any kind of ways you can think about bringing in executable code or modifying executable code, we can block. There's also a few other checks throughout the kernel that are pretty interesting. One of them, for example, is if you create an enclave. Enclaves are the Microsoft word for SGX, Intel's secure execution environment. Windows 10 supports SGX. Well, something that has arbitrary code guard enabled can't use SGX, because SGX is a way to get the CPU to execute code. Microsoft's smart enough to say, no, you can't use that. Or if you look at control flow guard, CFG, there's an API that lets you change the bitmap that makes CFG work. Well, someone who has arbitrary code guard enabled can't change the CFG bitmap. So actually some of the mitigations work together to make sure you can't bypass one mitigation when you're already being mitigated against a different mitigation. The last check is, of course, if you yourself have arbitrary code guard turned on, you cannot turn it off on yourself, nor can you turn it off on someone else. So if we're mitigating you, you can't unmitigate yourself, and you can't unmitigate someone else either. So there's a few checks to make sure that the mitigation is kind of broadly applied against potential bypasses. So how does someone use ACG? Well, if you're a developer, you can basically create a process with a special attribute that says, I want ACG, or your own process, if someone else creates it, if you don't control your own creation, can, at runtime, set on its own this mitigation. So I can say, I want to protect myself against dynamic code, or I want my children not to be able to have dynamic code. So there's kind of two ways of doing that. The other approach is if you're an administrator, someone doing IT in your enterprise. Then you can also, by using the registry, set image file execution options and set the right bit on the right process to disable this. So you can basically use the process name or the process path and say, that process, I don't want it to be able to get dynamic code execution. Now, this process was pretty complicated. You have to go in the registry, push out a reg file, use group policy. So in the new creators update, you can now use what they're calling Windows Defender Exploit Guard, which basically has a nice friendly user interface where you can basically check a box, put the process name, and it writes the registry keys for you, right? Because using the registry is hard. Now you have a nice user interface, and you just click a button and take care of that for you. So either developers can opt in, or an administrator can forcefully opt in a process into that. Now, there were bypasses around ACG already in specific contexts. Because, for example, one of the prime use cases for ACG is stuff that renders. PDF readers, browsers, Office. Unfortunately, browsers have JIT engines. They need to dynamically generate code. So do PDF readers. So does Office, right? VBA macros. So the top candidates for applications we want to protect with ACG happen to be the prime applications that have JIT engines. And JIT, by definition, is just-in-time compilation of new dynamic code. So in anniversary update, for example, Edge could not opt into this mitigation without allowing one of its threads to be the JIT thread. Meaning that if you compromise the process, you just have to compromise its address space to get to the thread that's allowed to JIT, and just abuse that thread or abuse what it was doing. So, as you know, threads aren't really security boundaries within the same process. So it helped a little bit. It made exploitation harder, but it wasn't a real boundary to say, no, Edge cannot create dynamic code. So they had to kind of address some of these issues in Creators Update Redstone 2, which came out of March of this year. And so what they did is this idea of out-of-process JIT. So in Creators Update, if you look at Edge with a tool like Process Hacker, you're going to see most of the processes, if you look at their mitigation policies, are going to say here, disable dynamic code. But one process, which Task Manager will identify as the JIT process, which is shown in this screenshot, doesn't have disable dynamic code. So there's one process that's allowed to JIT, the other processes are not. And the great thing about Chakra, which is Edge's JIT engine, is that it's open source on GitHub. So you can go on GitHub, you can see how they did this, and you can see the RPC channel between the JIT process and the content processes themselves. The content process, the JIT process, then has handles to all of the content processes, and it can basically JIT inside of their memory. Right? So ACG doesn't allow your process to dynamically generate code, but a separate process can go inside of your process and dynamically generate code as needed. Actually, there was a bug here that Google Project Zero found last month, which is that unfortunately the content process had a handle to the JIT process as well. And that's not very good because then the content process could open a handle, could use that handle to the JIT process and make the JIT process do whatever it wanted to. So they fixed that this month. So the JIT process can write into the content. The content's not supposed to be able to write into JIT, but took a while for them to fix that. There's also something called Warp, which I'm sure many of you are probably not familiar with. Warp is the Windows Advanced Rasterization Platform. And at parties, you should take shots and say that 10 times as fast as you can. This is the DirectX 11 software rasterizer. This basically looks at your video card, and if your video card can't do, I don't know, third-party quaternion time-shifting operations, it can JIT SSE or AVX code to do it on the CPU. Again, we have a jitter. So there's also a out-of-process warp JIT engine, which JIT's shader, high-level shader language, HLSL, into CPU assembly code if your GPU can't handle that specific shader that you're using there. So both the JavaScript engine and the DirectX software rasterizer JIT had to be taken outside of the process. And with this, now Edge can use ACG if you're on 64-bit, if you're using software rasterization, or if you have a WDDM 2.2 GPU driver. So there's a wide list of specific video cards that on 64-bit systems will get Edge to apply this. Because some older video card drivers or non-compatible drivers may still JIT on their own if they're not using the Microsoft rasterizer. And again, that would cause app compat issues. So for compatibility reasons, there is this flag that's set on Edge even today called allow remote downgrade. And with that flag, the master kind of Edge process can disable the protection on a content process if there's some sort of app compat issue. So there might still be ACG bypasses in the future kind of abusing this, because for app compat, which of course always trumps security, there still is a remote downgrade that's possible. So until they fully kind of clean that up, there might still be holes there. But we're not here to talk about remote downgrades, but just wanted to give you all the information on kind of how ACG works today. All right, so that's Arbitrary Code Guard. That's kind of what it's meant to do, and Edge and the Microsoft PDF Reader and lots of applications now have this. What does this have to do with Warbird? Well, Warbird is basically a very old technology. It's about 10 years old. It came out of Microsoft research. And what Warbird lets you do is obfuscate a binary. It has a few different ways through which you can do that, which I'll go over with. Now, Warbird is part of the compiler and the linker. So if you download Microsoft Visual Studio, if you disassemble the compiler, you'll see there's some undocumented Warbird options there, like what Warbird DLL to use, what Warbird configuration file to use. Completely different talk, but I think there's some interesting persistence and hooking things you could do in the compiler by pretending you're enabling Warbird, because you normally don't have those DLLs, and those compiler flags are not documented. But I think someone should look a little bit at that. So Warbird has a bunch of schemes to encrypt, obfuscate, or both a given binary. Now, in the most complex situation, what Warbird is able to do is it takes a function that you've written and separates into basic blocks, right? So before a jump, before any kind of indirect branch or comparison, those are your basic blocks. It then encrypts every single basic block with its own key. And then it destroys every piece of every control flow instruction. So your jumps, your calls, your rets, they're all destroyed, and basically have a bunch of encrypted blocks that are kind of stuck together with no control flow information whatsoever. The idea being that even if you reverse engineer this binary, and even if you find out how to decrypt it, you don't know where the basic blocks start and stop, basically, because you're missing all the control flow information, missing the beginning and the end of every block. Now, the actual control flow information is then built in a separate table that's obfuscated, and they use a number of tricks like forcing exceptions to happen or using breakpoints to silently redirect the application based on the right control flow. So it's kind of your standard anti-debugging, packer that basically Microsoft built themselves that most people don't know about. Now, Warbird can also encrypt a single function without breaking the basic blocks. So you can just have Warbird encrypt this function. So if I look at it in a disassembler, I need to know the decryption key to find out what it's doing. Or you can say, you know what, don't encrypt at all. Just make the function unreadable. So it has a very, very powerful obfuscator that basically makes the code extremely hard, if not impossible, to understand with static analysis. In fact, Hexrays, or the decompiler, would actually, in older versions, hang if you made it disassemble a Warbirded protected function. So it can either do encryption and kind of control flow destruction, it can do encryption alone, or it can just do obfuscation. And developers at Microsoft can use this technology based on what their needs are. And then you've got your typical anti-debugging, timing checks, and other kind of protection mechanisms that you would expect with this. So it's got a pretty fancy name, Warbird, and it's meant to be kind of the unifying technology Microsoft uses whenever they want to protect something. So what do they protect? Well, DRM. So Windows video files, when this used to be popular and they had a whole video store, came in these IBX files, which are individual black boxes, and the movies themselves were encrypted, and the decryption key was in a binary that was warbird obfuscated. Even today, the DRM platform files like mfplat.dll, for example, DRMK, and all of Xbox Live, if you look at those binaries, you'll see warbird. WinLogon, ever since Windows XP, which handled licensing and Windows activation for the first time, also protected by warbird. Today we have PEAuth in Windows Vista that does some of the authentication checks for licensing. And in Windows 10 you have clipsp.sys, which is the new common licensing infrastructure. All of this code is protected by warbird. But even at the kernel, if you look at ci.dll, for example, which handles code integrity and signing, if you look at PatchGuard, if you know what that is in the kernel, that code is also protected by warbird, but at different levels. For example, the kernel obviously is very performance sensitive, and PatchGuard, which does all these complicated checks, is even more performance sensitive. So if you look at PatchGuard, it's not encrypted in any way, but the code is merely obfuscated. While if you look at, say, PEAuth.sys, they're using full function encryption. So different binaries listed here have different kind of warbird schemes enabled. Okay, so in the old world, if you think of how kind of an unpacker works, in the cases where they're using encryption and basic block extraction, I have my DLL or my executable, and it's encrypted, right? So what I have to do is allocate, well, I have two options. Depending on the encryption scheme, I can either allocate some heap memory, make the heap executable, decrypt the code, and place it in the heap, and then run off the heap. Or maybe I can take the executable code, make it writable, and overwrite the encrypted executable code with decrypted executable code, right? So depending on my encryption algorithm, I can decrypt in place, or I have to decrypt somewhere on the heap. Well, with ACG, or with W XOR X, this is in direct contradiction, because you're either patching executable code, which violates W, or you're allocating new executable code and writing in there, which violates the X. So with ACG, warbird cannot possibly work. And why is that a problem? Well, it's a problem because we have DRM in our browsers. We have digital rights management, right? If you watch Netflix, there's a whole bunch of weird shenanigans and WebGL stuff and DRM authorization that works to make sure that, you're just watching Netflix in your browser, that it's not rendering, saving to disk, that HDCP is enabled, that your video card is using a protected output frame and all that stuff. You don't just get to watch movies online without a whole bunch of DRM around it. There's online games that use DRM as well when they run inside the browser. So there is a need to have digital rights management in your browser, and therefore there's a need to have warbird inside of some of the binaries that Edge uses. And not just Edge, but also if you think about other applications we want to protect, like games. We may want to disable arbitrary code generation in a game to make game exploitation harder, but at the same time, we need warbird in a AAA game work. So how can we make DRM, aka warbird, work if ACG is enabled? Well, we need something special, right? And the same applies for the shell, for game mode, all these binaries that are now protected in Creator's Update. They had to have some sort of backdoor, clearly, some sort of way that warbird was still able to function. Or maybe they just gave up on DRM. Maybe they said, people are not pirates, let's treat them with respect, and let's get rid of DRM. Not sure which one you think happened. All right, so let's go see what happened with warbird here. And every single time there is a new version of Windows, very simply what I do is I diff all the structures, all the enumerations, all the functions, and I try to see, what are some interesting changes in a new build of Windows compared to an old build. And I noticed this new information class, System Control Flow Transition. I said to myself, what is a System Control Flow Transition? So then I kind of went in IDA and I looked at what happens when we reach case 185. And I saw a call to a function called WB dispatch operation. And I had never seen functions with WB in the kernel. So I went to look in a little bit more detail. What kind of WB functions are there? And of course, as soon as I go in that function, the first thing I see is WB get warbird process. And then I see WB heap execute return, WB heap execute call, WB remove warbird process, a lot of interesting warbird functions. And I said, oh my God, they put DRM in the kernel. Great. All right, how can I abuse this? Because I looked at these functions, and there's no check for integrity level. There's no check for protection level. There's no check for are you admin. And of course there isn't, because a browser is the most unprivileged thing you can run on Windows, and a browser needs to enter this code path, right? So new attack surface to look into. So I looked at what WB functions are there, and of course I find this function, WB make user executable pages kernel writable. Like, that sounds interesting. That sounds exactly like what I would like to do. So I thought, can I trick Warbird into doing my bidding? Can I make it think that my payload is DRM code that needs to be decrypted? So I kind of looked at what's needed to do this, and I had to do a whole bunch of reverse engineering, and obviously, you're not going to read it off the slide right now, but there's this structure you have to pass in where you basically indicate some information about what you'd like to execute off the heap. And it's got a hash, which is pretty confusing at first, which is basically a hash of all your parameters. So you hash your own input argument, which is weird. And then a bunch of RVAs, relative virtual addresses to where the code is, the first stage, second stage, and then you have a key as well, and this round data that I'll talk about why that's useful. So there's kind of a way of asking a kernel, please execute stuff on the heap. Now, some of the stuff that's hard here, everything is done through relative virtual addresses. And then once you compute those relative virtual addresses and you fill out a data structure, you have to hash your own data structure and put the hash as part of the data structure. So kind of makes sense, because if you think about it, that data structure from earlier is probably embedded with the encrypted code. So the encrypted code has its kind of own descriptor, and then you kind of call a function to say, using this descriptor, please decrypt that code. But I wanted to do this at runtime, right? I didn't want to do this with the text section, or I wanted to do this off the heap itself. So the attack code basically has to figure all this stuff out, or use someone who's already figured it out. And the trick here was that the parameters structure, RVA, the relative virtual address of the parameters, is basically the beginning of the block. And then the first stage and second stage functions, which are the functions you actually want to run off the heap, they're actually based off the parameter structure. So this sounds pretty confusing, so I ended up making a picture which is even more confusing, but just to kind of show you, you're here, you have to point over there, then from there there's another offset to go to here. So there's a little bit of kind of figuring out exactly what the offsets had to be in order to actually get my code to execute. And of course, once the slides are online, it'll be easier to kind of follow this through. But the point is, there is some nicety here as well, because there's no absolute addresses, right? And one of the nice things when you're thinking of an exploit context is relative addresses are great. So Warbird is great from that perspective, because if you don't have to know where you are to get Warbird to work, as long as you know the relative addresses of the things you want to access. All right, so when you actually ask Warbird to execute from the heap, it basically makes sure that your data structure is valid, and it then creates a heap executed block. At that point, it checks if the SHA-256 that you gave it matches the SHA-256 of the parameters. Again, it's hashing your own input, and then you're specifying the hash of your input. Then it makes sure that the memory attributes of the function are valid. So the idea here was, if you're saying your function is some sort of like a non-executable function, then that's a problem. And then it creates user mode executable memory inside the process for you from kernel mode, copies your payload in there, and then executes your payload. But there's a problem. If Warbird is allocating executable memory in your process and you're calling it inline, the mitigation will return false. It'll say, hold on, Arbitrary Code Guard is turned on, you cannot generate executable code. So it turns out Warbird doesn't use NT-allocate virtual memory. It uses mi, allocate virtual memory, which is an internal function inside of the kernel, and it passes this undocumented flag, which only the kernel can pass, 0x 20 million, which I've called mem bypass ACG. And basically, the code inside the kernel says, well, if you're not bypassing ACG, then we're going to verify if we should block you. And of course, Warbird passes that flag. This check does not execute, and Warbird is allowed to allocate executable memory inside of your process. Then, after it does that, it creates what we call an MDL. An MDL is a way to take physical pages that reference a virtual address, remap a separate virtual address with different permissions, and basically takes the executable read-only pages in user mode and makes a kernel read-write version of those read-write-execute version of the pages so it can copy the payload in the kernel read-write-execute mapping, which of course is the same physical pages as the user mode read-only execute mapping. And now in user mode, you've got your payload in the heap allocated block. Then you have some cryptography that happens. At this point, because Warbird is meant to be used with encrypted code, it takes as input a 64-bit key, an initialization vector, and 10 seed values for 10 rounds. Because Warbird's encryption is what we call a Feistel network or Feistel cipher. And this is a pretty old kind of encryption technology kind of used for DES. If you remember DES from the 90s and 80s, it used a type of Feistel network as well. Keep in mind that Warbird was created, 15 years ago. DES and Feistel networks were pretty advanced at the time. And even today, a 10-round Feistel network is not going to be something that anyone can brute force. And each round of that kind of cryptography, you get a seed value. So you have to tell it the 10 round seed values, the initialization vector, and the key. With this information, it then decrypts your payload. Now your payload is decrypted. Then it's time to execute the payload. So what does Warbird do? Well, you called into kernel mode. When you call into kernel mode, you get a trap frame that says, where were you calling from? And what Warbird does is it edits your trap frame, it edits your context, and instead of returning back into where you called it, it returns into the heap block that it just allocated for you. So what's really nice about this undocumented system call is that not only it takes your payload, allocates executable memory for it, shoves it there, but actually as part of the system call, change it almost as like a long jump to your payload directly. So you don't have to ret or rup into your payload. The kernel does it for you, essentially. So this is pretty nice if we can find a way to abuse this. But there's a few challenges if we want to abuse this. First of all, our payload has to be encrypted, right? Because part of what Warbird does is it uses that Feistel cipher to decrypt the payload. So we have to find a way to encrypt our payload beforehand. And the second problem is we have to validate, we have to pass all the validation checks that Warbird is going to make. That's the easy part, right? Passing those validation checks. So of course, just send the data of the right size, make sure your RVAs are correct, hash your input data correctly, use an existing SHA-2 library, and then you're good to go. Well, except Warbird makes sure that all of your parameters are in executable memory. It actually checks, are you executable? Well, that's what it looks like it's doing, but if you actually disassemble the Warbird function that makes that check, it checks, are you executable or are you read-only? So if you're executable, it lets you send the parameter blob, or if your parameter block is read-only, then it also works. In the first slide, you might think, okay, but if your parameters are read-only, how can you hash your parameters and write the hash in the parameter block, right? It means that it's read-only memory. You can't do anything with it. But it checks, is it read-only memory right now? So, of course, what you can do is allocate some read-write memory, write the parameters and the payload inside of read-write memory, and you are allowed allocating read-write memory, right? There's nothing wrong with that. Then call virtual protect and make your read-write memory read-only once you're done writing into it, and then call Warbird. And Warbird says, is this memory executable? No. Is it read-only? Yep. Okay. I'm going to allow you to send code to me because it's read-only. So very bizarre kind of additional check they make. Why do they allow read-only memory? Well, good for us because that lets us solve problem number one. We still have problem number two, however. which is we need to encrypt our payload with a 10-round Feistel network, right? And 6 months ago, I didn't even know what a 10-round Feistel network is. So without having to rebuild our own Warbird encryption algorithm and make sure we match the one Microsoft wrote, can we use something else instead? Can we abuse this? Now, if we look at the Warbird functions, there is a execute, there's a return, there's a decrypt, and there is a re-encrypt. So you can decrypt encrypted code, or you can re-encrypt code. And I thought, great, I'll just put a decrypted payload, re-encrypt it, and now it's encrypted. But Warbird's not stupid. It's re-encrypt. So it actually has a decryption count. And when you first create a block, the decryption count is 0, because it says you're supposed to send me encrypted memory. So the decryption count is 0, and if you call re-encrypt, it says, well, you never decrypted anything, so there's nothing for me to re-encrypt. I can call decrypt, and now the decryption count is 1, and then I can re-encrypt. The problem is if you're thinking, oh, can I just put the plain text payload, call decrypt, and then call re-encrypt? You can't, because Feistel networks are not reversible ciphers. They're not like XOR, right? You can XOR a decrypted string and get the encrypted one, or you can XOR an encrypted string and get the decrypted one. But you can't Feistel decrypt something that's already decrypted. You'll basically get garbage data, and then when I re-encrypt it, I'll get extra garbage data. So that idea did not work. However, there's still a flaw. Because when they decrypt a segment and the decryption count goes to 1, they don't protect the virtual memory in user mode. There's actually an API call that you can use to do that, secure virtual memory, which basically says now that someone in kernel mode has done something to this memory, nobody in user mode can modify it, but they don't do that. Therefore, you can decrypt a segment and then in user mode write anything else you want on top of that data, and then you can call re-encrypt. In other words, we can allocate some read-write memory, leave it blank, ask Warbird to decrypt it. There's nothing there. Now we get a bunch of garbage. Overwrite the garbage with our actual payload in plain text, and then ask Warbird to re-encrypt. And re-encryption will work because Warbird thinks, oh, I decrypted that earlier. And now you have correctly encrypted the payload. And you can use this as part of an attack, inside of the browser, do that right now, or just at home as the attacker, use this technique to have your payload pre-encrypted, and then just drop the payload pre-encrypted. So basically, we can actually abuse Warbird to encrypt the payload for ourselves. So both of these challenges are solved. We can now basically abuse the Warbird technology for ourselves. And I'll give you a sample of basically how this looks. So the idea is, I've bypassed ASLR, I have ROP, right? Our basic assumption is we have these two tools available. I only need to call virtual protect once to make something read-only. So I just find some memory somewhere, put my encrypted payload in there, call virtual protect to make it read-only. Then using, again, ROP and ASLR, call NT-set system information with this new undocumented Warbird class, and now I can execute the code that's there. I can also just encrypt it myself with any key that I want, any IV and any seed data, or bring in existing encrypted payloads as well. At this point, Warbird will execute my payload. It will bypass ACG. And basically, other than that, I can also just use Warbird as an unpacker. Right? Forget about ACG. You now have in the kernel a technology that lets you take encrypted executable files that you can control as an attacker, as a bad guy, and have the kernel unpack them for you. Right? And good luck all unpacker technologies when the kernel's the unpacker now. Right? Now you need a kernel debugger to see what's going on. So yes, there's an ACG bypass here, but also kind of from a visibility and forensics perspective, why does the kernel need to have an unpacker? Well, DRM, of course. So basically, the example I'm going to show you is going to be very simple. I'm going to put the payload at offset 0, and I'm going to put the parameters right after the payload. Then I'm going to encrypt the payload with a key of 0, initialization vector of 0, and the seed data as all zeros. What this lets me do is have pretty much just zeros for almost all the parameters. And of course, when you call virtual alloc to allocate a page, it comes full of zeros. So this just makes the exploit very, very small. Then the only thing I need to do is to memcopy that static kind of payload into that read-only page, which of course I'll make read-write for a little bit, and then feed that to Warbird, and we're good to go. So I know this is too small to read right now for the audience, and just to show you that basically it fits into a slide, including comments, right? We have 1, 2, 3, 4, 5, 6, 10, 12 lines of C code are all that's needed to basically execute the payload. And in assembly, this is 245 bytes, including kind of fancy comments. And the payload itself, which here will look to you just like a bunch of hex, there's my encrypted payload with a key of 00000, and there is the SHA-256 of a bunch of zeros, right? Because my parameters are all almost 0. So a hash there, which I can compute on the attacker machine, the encrypted payload, which I compute on the attacker machine, and this is basically 120 bytes. Right? So I just have to shove this somewhere in some static buffer, wrap into virtual alloc, wrap into memcopy, or just do memcopy in assembly code, wrap into NT set system information, and I've got basically code execution. Right? And we'll see if I can make it on time, and I'll do a demo at the end. But hopefully you trust this does actually work, and I'll publish the code as well a little bit later on. But just to make sure I don't miss time, I do want to talk about the fix that was actually done first, and then we'll see if I can show you on the Mac after that. Because how do you fix this? Right? This is a design level flaw in the kernel, in my opinion, where you've made the kernel an unpacker now. Well, there was a function there that did that check. Are you execute read-only, or are you read-only? Which now in Redstone 3, in Fall Creators Update, is seen as a WB verify virtual address signature. And this now checks, are you executable? It no longer checks, or are you read-only? So unless you can grab executable memory somehow, which is in violation of ACG, you can't use Warbird anymore. And this seems like a pretty solid fix, but it will be incomplete. Because if I can still somehow trick IE or Edge into loading a DLL from the disk that I own, a low-integrity, untrusted DLL, maybe from a network share or something like this, I could still, in that DLL, have malicious encrypted code. So that fix would kind of mitigate most of the ACG issues, but it would still leave it open to abusing the kernel as an unpacker. And so the second fix that was done is to check the signature level as well. And what is the signature level? The signature level is basically a concept that Microsoft added in Windows 8 that looks at the certificate of a binary and its EKUs, its enhanced key usages, as well as the signer. For example, Microsoft has a signature level. Windows team within Microsoft has a signature level. Joe Bob doesn't have a signature level, but Joe Bob signed by Symantec has a signature level. So now we can actually check the signing level or signature level of the DLL that contains the Warbird encrypted payload. And since only Microsoft should ever use Warbird, and since only Windows components should ever use Warbird, the second check is quite simply, are you sending me data that's A, in an executable block, and B, is it currently being stored on a DLL that is signed by the Windows team at Microsoft? And with those two checks, basically, the function now has a compare signing level check right here, which kicks out anything that's not a Windows signed DLL, and we've changed the check that we had here earlier to only look for execute read and not for read only. So we really needed both of these fixes to address the problem. And of course, nothing's that simple, because to get the signing level of a DLL, how do you do that? Well, you couldn't do that in Windows before. There's no function to let you do that. So I actually had to change a data structure to add a flag there that lets you get this information. And so this is where we have to get into the scope of the fix. How hard was it to add those 2 lines of code, right? You're all looking at it saying, 2 lines of code, they fixed that in 2 weeks, right? Well, it took them 11 months to fix this bug. Because the memory manager, and if you work at Microsoft, touching the memory managers, like you do that once a year, you make a prayer, you hope it works, and then you made your change to memory manager. To make the memory manager get that signature level and actually use it. Then all the DLLs that contained Warbird code had to be signed correctly so that Windows would see them as Windows signed DLL. So they had to check all the signing settings across their whole build environment. And then the Warbird compiler had to be changed to generate things in executable sections all the time. Because, of course, the reason why there was a check for read-only or executable is because sometimes Warbird generated those blobs in your .r data section, which is read-only data and not only executable. So changing all of these things basically meant that I got an email that said, we can't issue a CVE, we can't issue a patch for this. People will have to wait until fall creators update. This requires a new version of the OS. That's how complicated the fix is. And so as of today, if someone were to kind of use this attack, it would still work just fine. We have to wait until October, download the fall creators update when that comes out, and that's going to fix this issue. So there is no patch available, basically, due to the complexity. All right, so kind of some parting thoughts on this. Crazy to me that there's basically now a backdoor in the kernel to unpack code and bypass mitigation. Crazy that so much work was put in by lots of people at Microsoft to basically make DRM technology work in a situation where it shouldn't. You'd hope that by today, DRM doesn't undermine security or doesn't kind of trump security, but of course that's naive, it still does. End of the day, it's good that Microsoft fixed this, good that they issued a bounty for this, which I was very happy with, but still kind of sad that DRM is still there today. So if you're interested in more, obviously I'll be around. You can ask me questions if you see me later on. I'll also be talking about this at Blue Hat, specifically about some issues with the bounty program that I kind of uncovered as reporting this to Microsoft during the 11 months that the whole saga took. And once that presentation is done in Seattle in November, I'll be posting these slides, those slides, a GitHub repository, so you can play with Warbird as well and kind of try to see what are other fun things that we can do there. So this bypass will be fixed, but there's still an unpacker in the kernel, and so maybe there's some more interesting things to see there next year. All right, but that's the bird that killed ACG, and if you want to know a little bit more, there's some good blogs from Microsoft on ACG itself, the Google bug. Again, you'll have these references once the slides are posted. So without further ado, thank you very, very much. It's good to be here in Buenos Aires. I appreciate it.